Here we are. All right. This formula has to do with separation of variables. I will show how on Friday because I want to get through this in the time that I need to get through it. But the idea here, a lot of this should actually be a little bit of review. The reason we're doing it is because the formula here comes from separation of variables. And so that's why we're talking about it. And that is this formula right here. Y equals y naught times e to the kt. Again, hopefully you know all this information already. But y naught is the initial condition or a starting amount. K is some constant that depends on the rate of growth or decay. And then T is time. So usually what we're going to need to do is we're going to have an initial condition, and we are going to use that initial condition and another point on this graph to solve for K. That's usually what's going to end up happening. So let's dive into some examples here. Colony starts with 1 bacterium and doubles in number every half hour. How many bacteria will remain at the end of 24 hours? So, first of all, starts with 1 bacterium, so that's our starting condition, initial condition. That's why not. One times e to the kt. And now we're going to use the other point that we have in order to solve for K. So what is the other point that we have? It doubles every half hour. That gives us a point. That tells us that how much there is after how much time. 30 minutes or a half hour. This is going to go in hours, so when t equals 1/2, how much is there? It started with 1, and then it doubled. So now it's 2. That was a toughie. One times 2 is 2. When t is 1/2, after a half hour, the amount that we have is 2. We started with 1, so if I double it, it's 2. All right. You could probably figure this one out without this element, but this is meant to be the easy one to kind of ease us into this. So we talked and practiced through rewriting natural logs a lot yesterday. Now we're going to be rewriting it the other way because we need to solve this for K. This tells us if we rewrite it, natural log of 2 equals 1/2 K. that? So e is my base here. Here's where my exponent goes. And then 2 is the argument of the natural log. So k equals 2 natural log of 2. Y equals e to the k times t. So our function now is that k is 2 natural log of 2 t. So if we want to know how much there is at the end of 24 hours, then we're going to plug in 24 for t. And I'm going to do some simplifying to get the answer that you probably will expect. E to the natural log of 2 2 times 24 is 48. Okay, with that rearranging, E, if I take something to the A and raise that to the B, then that's the same as raising it to the A times B. So I'm rewriting it. I'm rewriting e to the natural log of 2 times 48 as e to the natural log of 2 to the 48. And I'm doing that because e to the natural log of 2, as we discussed yesterday, is 2. So the answer is 2 to the 48. Which hopefully you expected that answer. Because if we're doubling every half hour for 24 hours, how many times are we doubling? Well, we're doubling 48 times. And we started with 1. So again, fairly easy problem that you could have probably come to without E. But the nice thing about E is that we can generalize for any exponential growth. We don't need to worry about what to put in the base and all that kind of stuff. It's going to follow the same process every time. So we can kind of standardize things by using E, and using natural logs is easier than worrying about solving with logs for a base. Let's do a couple more. Well, this time we have the equation. Ignore the assignment. I'll have a homework assignment for you later, but not right now. Decay equation is known to be y equals y naught times e to the negative 0.18t. With t in days. About how long will it take for the amount of radon in a sealed sample to decay to 90% of its original value? Oh, notice the question it's asking is how long. How long will it take? So that means we are solving for t. We're trying to solve for t. So that has to mean that we must know y and y naught. We already know k, which will leave us to be able to solve for t. Well, let's take, if our starting amount is 1, after this amount of time that we're trying to solve for, if we started with 1, how much is left? 0.9 is left. Because it says we want 90% of the original value. So the amount that would remain would be 0.9. Natural log of 0.9 equals my exponent, which is negative 0.18t. So if I solve, that means t is the natural log of 0.9 over negative 0.18. Which I'm sure you all have memorized in your head. You guys memorized the log table in pre-calc, right? I'm just kidding. You get a calculator. So in the calculator. Next week, quiz on the natural log table. They had to know how to do logs before the calculator. So you'd get a table. So they would use techniques to compute the values. And then when you did logarithms, if you wanted the log of 2 or the log of 3 or the log of 4, then you would look at a table that would give you those values to like 4 decimal places. You would change the base. You would do log of 0.9 over log of e. Yeah, it would look pretty similar to like your z-score table, those of you who took stats and t-scores. It's that same idea. No, Olivia. All right, anyway. Just... .5853. Days. We're going to label our answer. Questions on that? All right. Next one. I need to open a new document. Actually, you know what? I can use this. Here we go. Suppose an exponential population of fruit flies increases to the law of exponential growth. There were 100 flies after 2 days and 300 flies after 4 days. Approximately how many flies were in the original population? So this time, we're trying to solve for, why not? So that's our equation that we're trying to solve for. And this one's going to be a little bit more complicated. Because we also need to figure out what K is. So the good news is we have 2 points to use. After 2 days, we have 100. And after 4 days, we have 300. So those are our 2 points. So we're going to need the E part by itself so we can rewrite. And I'm going to do the same thing over here. Oh, you know what? Easier way to do this. I missed this. I forgot. We're going to do substitution. We're going to do substitution, which is we're going to get y naught by itself in that red equation and then plug it into the blue equation, or in the green equation. I wasn't looking and I forgot what color I was using. One second. Yes? I'm saying, are we good with that? All right. So that means, in this equation, instead of y naught, I can write 100 over e to the 2k. And this is not going to be as messy as it looks because e to the 4k over e to the 2k is going to be e to the 2k. So we're going to be canceling some of the fraction. Oops. Rewrite with natural log. Okay, here's what happened. You guys didn't see it. Here's what happened. Usually there's a sensor bar for each of these markers in the eraser. And it takes, I have both of these in my hand. So it took the thing I most recently picked up. So usually that would be the fact that I picked the eraser up and it would erase. Now the light's on because I reset it. But what happened was I picked up the eraser and a little ladybug has been crawling around my smartboard all morning. And it just so happened that when I picked up the eraser, it was crawling around right inside the sensor. And so it's like, you still have the eraser in here. And decided that to keep using the marker. It works. Rewrite with natural log. So k equals natural log of 3 over 2. We're going to get a decimal. .5493. Yeah. So back to this equation. Yeah, let's do the one sorry solved. Good idea. 100 over e to the 2 times, what was our decimal for k? 0.5493. So plugging it in up here. 100 over e to the 2 times that decimal. So we're going to do 100 over e to the 2 times that decimal. Well, that decimal was the last answer I called up, so I'm going to go second and answer. 33.3 repeating. 33 and a third. What's our units here? Flies. Mm-hmm. If you want to round it, they'll take a rounding. Yeah. Questions?